Hello everyone, welcome to the course on Basic Electronics 23 CT 23B. Myself Umayas. We're discussing about Module 3 Integrated Circuit Operational Amplifiers and its applications. So here are the contents. So in this session, we'll be discussing about non-inverting amplifiers and the inverting amplifiers. Coming to the non-inverting amplifiers. So the first one is direct coupled non-inverting amplifier. The non-inverting amplifiers circuit is as shown here. It behaves similarly to a voltage follower circuit with one major difference. Instead of all of the output voltage being fed directly back to the inverting input terminal as in a voltage follower, only a portion of output voltage is fed back. The output voltage is divided by the resistors R2 and R3, and the voltage across R3 is applied to the inverting input terminal. As in the case of the voltage follower, the output voltage changes as necessary to keep the inverting input terminal voltage equal to that at the non-inverting input. Thus, the voltage VR3 always equals Vi, and the output voltage is then determined by the resistances of R2 and R3. Because the signal voltage is applied to the op-amp non-inverting input terminal, the output always has the same polarity as the input. A positive going input produces a positive going output, and vice versa. Thus, the input is not inverted here, and the circuit is identified as non-inverting amplifier. The voltage divider current I2 is always selected to be very much larger than the operational amplifier input bias current, and VR3 is equal to Vi is equal to I2 R3. Also from the figure, it is seen that current I2 can be given as V0 by R2 plus R3, and the circuit voltage gain is given as ACL is equal to V0 by Vi is equal to I2 into R2 plus R3 divided by I2 R3. So the equation for ACL will become R2 plus R3 by R3. So therefore from the equation, the circuit which shows a non-inverting amplifier circuit with a resistor R1 that is connected in series with the non-inverting input terminal. As in the case of other op-amp circuits, this is done to equalize the resistor voltage drops produced by the input bias currents. In this case, R1 is chosen to be approximately equal to the resistance seen looking out of the inverting input terminal. Thus, R1 is becomes equals R1 becomes equals to R2 parallel R3. The input and output impedances for a non-inverting amplifier are easily determined from the negative feedback equation. Design of a non-inverting amplifier mostly involves determining suitable voltage divider resistors, that is R2 and R3. So the design begins with the selection of a voltage divider current that is much larger than the op-amp input bias current. So because the signal voltage is applied to the op-amp non-inverting input terminal, the output always has the same polarity as the input. So a positive going input produces a positive going output and vice versa. Thus, the input is not inverted and the circuit is identified as a non-inverting amplifier. The voltage divider current I2 is always selected to be very much larger than the operational amplifier input bias current. So these are the set of equations for the circuit. Coming to the capacitor coupled non-inverting amplifier. When a non-inverting amplifier is to have a signal capacitor coupled to its input, the op-amp non-inverting input terminal must be grounded via a resistor to provide a path for the input bias current. So this is shown in the figure where R1 allows for the passage of IB1 as in the case of the capacitor coupled voltage follower. The input resistance is essentially equal to R1 for the capacitor coupled non-inverting amplifier. So the resistors R1, R2 and R3 in the capacitor coupled circuit are determined exactly as for a direct coupled non-inverting amplifier. The capacitor values are calculated in the same way as for a capacitor coupled voltage follower. So here this circuit diagram shows a capacitor coupled non-inverting amplifier circuit must have the non-inverting input terminal grounded via a resistor to provide a path for the input bias current. So this is the here we have two circuits. One is non-inverting amplifier circuit with resistor R1 in series with the input. R1 is selected to be approximately equal to R2 parallel R3. A capacitor coupled non-inverting amplifier circuit must have the non-inverting input terminal grounded via a resistor to provide a path for the input bias current. So next we have inverting amplifiers. Inverting amplifiers. First one is direct coupled inverting amplifier. So this circuit is termed as inverting amplifier because with V1 applied via R1 to the inverting input terminal, the output goes negative when the input goes positive and vice versa. Note that the non-inverting input terminal is grounded via resistor R3. With the non-inverting terminal grounded, the voltage at the op-amp inverting input terminal remains close to ground. Any increase or decrease in the difference in voltage between the two input terminals is amplified by the op-amp open loop gain between the two input terminals is amplified by the op-amps to open loop gain and feedback via R2 and R1 to correct the change because the inverting input terminal is not grounded but remains close to ground. The inverting input terminal in this application is termed as a virtual ground or virtual earth. So the circuit input current in figure can be calculated as I1 is equal to VR1 by R1. So the input voltage is applied to one end of R1 and the other end of R1 is at ground level consequently. So VR1 is equal to V1, I1 is equal to VI by R1. I1 is always selected to be very much larger than the op-amp input bias current. So virtually all of I1 flows through resistor R2, and the voltage drop across R2 is VR2 is equal to I1 R2. The left side of R2 is connected to the op amp inverting input terminal, which is um, always at ground level. This means that the right side of R2, the output terminal, is VR2 below ground. So V0 is equal to minus I1 R2. So from the equation, Vi can be written as I1 R1. Therefore, the circuit voltage gain ACL which is the ratio of output voltage to the input voltage, becomes equal to minus I1 R2 by I1 R1. ACL is equal to minus R2 by R1. If the input of the inverting amplifier is grounded, the circuit is seen to be exactly the same as a non-inverting amplifier with R3 as the input resistor and zero input voltage. Thus, negative feedback occurs to maintain the op amp inverting input terminal at the same voltage level as the non-inverting input terminal. The output impedance of an inverting amplifier is calculated in exactly the same way as for a non-inverting amplifier. As in the case of the non-inverting amplifier, the output impedance is very low for an inverting amplifier. The input impedance of an inverting amplifier is easily determined by recalling the right side of R1, which is always at ground level, and the signal is applied to the left side of R1. Therefore, Zi is equal to R1. Design of an inverting amplifier is very simple. Voltage divider current I1 is selected to be very much larger than the op amp input bias current. Resistors R1 and R2 are calculated from the equations which we already discussed, and R3 is chosen to be approximately equal to R1 parallel R2. So any increase or decrease in the difference voltage between the two input terminals is amplified by the op amp open loop gain and fed back via R2 and R1 to correct the change. Because the inverting input terminal is not grounded but remains close to ground, the inverting input terminal in this application is termed as a virtual ground or virtual earth. So the current I1 will become equal to VR1 by R1. The input voltage is applied to one end of R1 and the other end of R1 is at ground level. Consequently, VR1 is equal to VI, I1 is equal to VI by RI. I1 is always selected to be very much larger than the op amp input bias current. Consequently, virtually of all of I1 flows through the resistor R2, and the voltage drop across R2 is the left side of R2 is connected to the op amp inverting input terminal, which as discussed, it is always at the ground level. That means that the right side of R2, the output terminal is VR2 below ground. So these are the equations for open loop, closed loop voltage gain, that is ACL is equal to minus R2 by R1. If the input of the inverting amplifier is grounded, the circuit is seen to be exactly working as same as non-inverting amplifier with R3 as the input resistor and zero input voltage. Thus, negative feedback occurs to maintain the op amp inverting input terminal at the same voltage level as the non-inverting input terminal. The input impedance of an inverting amplifier is easily determined by recalling that the right side of R1 is always at ground level and that the signal is applied to the left side of R1. Next is capacitor coupled inverting amplifier. The capacitor coupled inverting amplifier circuit is as shown. In this case, the bias current to the op amp inverting input terminal flows from the output via resistor R2, so that the input coupling capacitor does not interrupt the input bias current. A voltage drop IB R2 is produced at the inverting input by the bias current flow, and this must be equalized by the IBR3 voltage drop at the non-inverting input. Therefore, for the capacitor coupled non-inverting circuit, apart from the choice of R3, the circuit is designed exactly as the direct coupled circuit, and the capacitor values are calculated in the same way as for a capacitor coupled non-inverting amplifier. Thank you.